So yesterday we looked at the formation and all of the steps it took to form an ionic compound. And so there's some extra parts of chapter 8, but I didn't think they were necessary. We're going to go right into formation of a covalent compound and what that looks like and how much energy is required to form that covalent bond. Okay, or to break covalent bonds or whatever, right? We looked at bond dissociation in the Born-Haber cycle and how much energy it required to break bonds of diatomic molecules. But now we're going to look at what has to happen for a covalent compound really to form, okay? And different energies that are found in different types of bonds, how bond length is affected by, how bond energy is affected by bond length, right? We're going to look at that a little bit too. So this should be a pretty common sense statement, right? In order to break bonds, energy has to be added to the system. Do we understand why that's the case? If I'm going to break bonds, I need the molecules to start moving, right? They start moving faster and faster and faster so much that those bonds break, right? That's the basic definition of what has to happen there. And the opposite then should also be true. To form bonds, energy is released, okay? So that's not something that we usually think about, but it is true, okay? So the bond energy of a particular bond between two molecules is given with this formula, delta H equals sigma N times D. That's a lot of stuff, okay? And then it's minus, so it's basically the amount of energy in bonds broken minus the amount of energy in the bonds that are formed. Okay, so we'll kind of see what that looks like. Here's our definition for each. Okay, and then I'll walk through these once you guys get them written down. Yeah, that's a Greek letter. Do you know what Greek letter that is? Sigma. It's called sigma, right? And it means like the sum of all of the things, okay? So sigma means the sum of all of the terms. So if we have 4 bonds that have to be broken to form something new, then we have to add all 4 of those bonds together before we subtract out the energy of the bonds that were formed. Does that kind of make sense? So it's like the total of all the broken bonds minus the total of all the formed bonds. Right? That's all sigma means. Okay? N is your mole coefficient. Okay, and so I'll show you kind of what that means here in a second. Essentially what we're going to look at for these formation of covalent compounds is to form whatever compound we want, we might have to break down a certain molecule and then build it back up and reconfigure it, right? That's kind of what we're looking at. Is we're going to take all of the atoms from a certain molecule, reconfigure them, and form the new bonds that we want. Okay, because realistically, carbon doesn't exist in nature just kind of by itself. Okay, carbon was a bad example because carbon does do that. But some nonmetals don't just exist by themselves in nature, right? And so in order to extract them to bond with other nonmetals, we would need to literally do that, extract them from other compounds, okay? So the carbon example was a pretty bad one. But some nonmetals we need to take out of other compounds to be able to get them where we need to be. So that's essentially what we're looking here is we're going to have to break down a molecule and build up a new one, and we want to see what's the energy transfer that happens when that happens, okay? So D is energy of the bond energy per mole. We're going to have to, again, be looking at mole ratios, and we're also going to have to be looking at how many of a particular bond is in a compound, okay? And that'll make a little bit more sense here when we look at an example. So let's dive into our first example here. We want to calculate the change in enthalpy of the following reaction. Okay, we have a compound, CH3N, and then C. What's that? Do you know what that is? Yeah, what's it look like, though? It's more than just a single bond. It's a triple bond. So the reason it's written like that is to just tell you something about its Lewis structure, that there's a triple bond there that we're going to have to break. Okay, so not all molecules give us a clue into the Lewis structure, but this one does. Okay, and then all that's happening here is we're reconfiguring now. Instead of the nitrogen being bonded to this group of carbons, now this carbon is being bonded to that group, and the nitrogen is then attached to that, right? So the carbon and the nitrogen are essentially switching spots in this new formation. So how we calculate delta H is we're going to take, right, the amount of energy from the bonds broken here minus the amount of energy it takes to form those bonds. Okay, so let's just go ahead and start looking at this molecule. here's the bond energy of each of the types of bonds we have present in the molecule. So in order to complete these problems, we have to be able to kind of visualize what the Lewis structure looks like. We don't have to fully draw the Lewis structure yet, but we have to envision a little bit. Do you know what I mean when I say Lewis structure? Let me like jog your memory here. So C, H, 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 N, C. That's what this one would look like, right? Do you know what I mean when I say Lewis structure now? Okay, it's like the two-dimensional kind of image of what that would look like. So in this particular structure, I know that I have 3 of these bonds, right? Does that make sense? In this structure, I know I have 3 CH bonds. Would I be able to tell that without drawing the molecule out? Yeah, I could, right? Just based on H3 right here. I know we've got 3 of those hydrogens surrounding that carbon. So I've got 3 of those bonds. How many carbon to nitrogen bonds do I have? This type. Just one, that guy right there. So I've got 1 of those. Do I have a carbon to carbon bond in this molecule? I don't, so I'm not going to worry about that yet. But I do have a carbon triple bonded to a nitrogen. I've got 1 of those. Does that kind of make sense? So we're going to be listing out these bond energies similar to what we did in the Born-Haber cycle, but it's just a different process, right? We're still going to be adding all of these together. So for the reactant side, I'll take 3 times 413, and that gives me 1239. We are going to need our calculators today if you don't already have those out. Okay, 1239. And then I need 305, and I have an 891. So the total amount of energy needed to break all of those bonds, we're going to add all those together, plus 305, 891. That gives me 2435 kilojoules needed to break those bonds. Okay, does that part make sense, how we found that?
Now you said something about subtracting.
Right, we're going to do that in a second.
Okay.
This is the amount of energy required on the left, on the reactant side.
Okay.
Okay? Now we're going to look at the product side. Without drawing out the molecule, let's see if we can identify the numbers of bonds in the molecule. So, looking at our products, how many carbon to hydrogen single bonds will we have?
Carbon, 3.
Right, we're still going to have 3. Those 3 hydrogens are still bonded to that carbon. Are we going to have a carbon to nitrogen single bond here? No, right? We don't have anything right there. Do we have a single carbon to carbon bond? Yeah, because this carbon has to be attached to that one. Okay, so we've got 1 of those, and then do we still have a triple bond carbon to nitrogen? Yes, so we still got 1 of those. So our values really are pretty similar. So 1239 there, 347, and 891. I'm going to add all those together, and I get 2477 kilojoules. So it required 2,435 kilojoules to break the bonds of our first molecule, and it released 2,477 kilojoules when those bonds formed again. And so now comes the subtraction. So delta H is found by taking the reactants total minus the products total. Okay, so delta H is always going to be reactants minus products. So this will tell us if our overall reaction is it endothermic or exothermic, right? That's what it's telling us here. So in this case, is our reaction endothermic or exothermic? It's exo, right? Because heat's flowing out of our system. Very good. Okay, questions about what that process looks like? We're identifying the numbers and the types of bonds that are found in covalent compounds. We're breaking them down and then restructuring them to build them back up, right? That's what we're looking for. Let's try, I think maybe I have one more example in the slides here. Yeah, one more. And then I have a table for you here that's got all these different bond energies. I'll give you that so that you have that for your homework. You're not having to look back and forth. But I do have a table here for you. Otherwise, I think in the problems, I just give them to you. Okay? Using the following bond energies, calculate the change in enthalpy of the following reaction. Okay, so here we've got 3 different products and we've got 3 different reactants. Okay? So let's go ahead and just start examining the first one. CH4. What type of bond is found in that one? Right? It's got to be a CH bond. So we're looking here. And then how many of those bonds do we have? 4. So I'm going to go ahead and just write, here's my CH bond. It equals 413, and I have 4 of them. Right? And then I can go ahead and give that total right there if I want to, or I can wait till later. But I kind of like to find an organizational method that works for me, right? So 413 times 4, 1652. Thank you. All right, second molecule. I've got a Cl2 molecule. So what type of a bond is that? Cl to Cl. And how many of those bonds do I have? I have 2 of them because I have 1 bond per molecule. And I have 2 molecules of it. Does that part make sense? That comes from that mole ratio right there. Okay, so I've got 2 chlorines bonded together, and that value is 239. And I've got 2 of those bonds that I need to break. Okay, so if the coefficient right here would have been 6, I would have had to multiply it by 6. Okay, does that part make sense? Okay, 239 times 2 is 478. All right, and then I've got the same thing here with fluorine. So it's a fluorine to fluorine bond. That value is 308. Oh, no. Sorry, 154. Yeah, 308. And then when I multiply it by 2, that gives me 308. Sorry about that. Okay, any questions about how I got those numbers, how I manipulated them? Okay, let's go ahead and add up that side, that total. All right, now the second side, we're dealing with our products. I've got CF2Cl2. How are those going to be attached? What types of bonds will I have?
Can you have 2
CF and CL? Just list them.
Yeah, so this is what the molecule would look like. I would have C, F, F, Cl, Cl.
So it's all in the same line?
Yeah, well, we're going to list out the bonds separately. I have a bond that is carbon with fluorine, and I have a bond that's carbon and Cl. You know what I'm saying? And I really have 2 of each of those types of bonds. Does that make sense? I've got 2 fluorines bonded to carbon and 2 chlorines bonded to carbon.
Did you say the fluorines are bonded together as well?
They're not bonded to each other. They're bonded to carbon. Yeah, because the molecule looks like... Sorry, I'll make this a little bit smaller. Molecule looks like that. Right, I've got carbon with 2 fluorines attached and 2 chlorines attached. So the fluorines are not attached to each other, and the chlorines are not attached to each other. They are attached to the carbon.
So are we supposed to know what it looks like?
You should be able to know from this part, just from the structure right here, how it's attached. These would be attached here. CF2, Cl2. We would know we've got both fluorines attached to carbon, both chlorines attached to carbon. Is that part what you're struggling with, is how to know what it's going to look like in 2 dimensions? Right. When we see a molecule that has carbon, it automatically goes in the center. Automatically goes in the center of our molecule. And then whatever comes after is what's attached to it. So I'm going to have a fluorine, chlorine, and chlorine. Right? If we have carbon, it's always going to go in the middle. Bless you.
Thank you.
But if you ever need help with this part of it, just ask me and I can help you with the skeleton part, because we're going to get to that, but it doesn't come until a little bit later. But for right now, if you need help with what that's going to look like, just let me know. All right, so then moving into our HF, what type of a bond is that? It's just HF, right? And we have 2 of them. Sorry, I didn't finish my values on the last one. This one was 485, and I had 2 of them. Chlorine to carbon bond was 339, and I had 2 of them. Hydrogen to fluorine bond is 565, and I had 2 of them. And then what's the last type of bond we have here? H to Cl, which is 427, and I have 2 of them. So then we're going to add up that whole products side. Oops. $36.32 was my total for my products. And so now to find the change in enthalpy, I will take 2438 minus 3632, and I get negative 1194 kilojoules. Okay, so that's the change in enthalpy of the entire reaction, right? It's not just the change in enthalpy of like one particular compound, it's the change in enthalpy of the entire reaction. And we know that for the entire reaction based on how much energy it was required to break and to then rebuild our new bonds, right? That's how we know how much energy was required for this particular reaction to take place. But it has to deal with all covalent compounds, and so we're able to look at how much energy was required in each of those bonds.